Let's talk about sequences. As we start chapter 11, I want to point out that what we talk about for the first few sections of this chapter aren't going to seem like they have anything to do with calculus or anything we've talked about so far this semester. But I promise after a few sections, it'll kind of land back in the land of calculus. Okay, so first we start off with a definition of what a sequence is. A sequence is an ordered list of numbers, and I've kind of specified here that list is going to be an infinite list of numbers. I have two examples on the screen here. So we could have a list like 2, 4, 6, 8. It's an infinite list of numbers, so we can't actually list them all. So typically we list maybe 3 or 4 or 5 of the terms so that you get a sense of the pattern. And then we have this ... at the end to say, and the pattern continues. Right, so it looks like I have even numbers, so I would assume the next number on the list is 10 and then 12 and so on. I also have a list here. I have 1, a third, a ninth, and so on. And again, we list enough so that we think the viewer kind of gets the sense of the pattern, and then we put in a ... I typically like to have 3 or 4 terms in the sequence, depending on what it is. So let's talk about kind of terminology. So usually our terminology, or notation, I guess, is like this. So when I say a sub n, it's supposed to represent the nth term of the sequence. So for example, a1 is the first term in the sequence, and then you have a2 is the second, a3 is the third. And the advantage of having notation like this is that you can very easily shout out, let's say, the 100th term in the sequence by just writing a sub 100 as the n value. And then we can call on our terms very easily. Now, there are a couple different ways to display and kind of get across what your sequence is. So we'll call this ways to display or define your sequence. And the first way is the way that we already see on the screen here, which is just a list of numbers. Remember that when we say an ordered list of numbers in this definition, that means that the order they're listed in is relevant. So if you took these same even numbers, but started listing them in some other order, like 2 and then 6 and then 8 and then 4, that's actually a completely different sequence than the one we're seeing. Okay, so aside from listing out the numbers, another way to do it is to provide a formula that creates the terms of the sequence. So you'll have a formula in between these two curly braces. Sometimes you see it without any other notation aside from that, but most of the time you'll have n equals, I'm going to say a 1 here and an infinity up here. And I just want to make a note. The n value starts at 1 unless otherwise stated. So this presentation here tells us the first value of n is 1, and then we know that n is only integers. So we say, oh, okay, so the next one is 2, the next one is 3, and so on. This infinity will always be here because that tells you don't stop your list, you just go forever. It is possible that we could have put n equals, let's say, 2 here. And that just tells us that a2 represents the first term in the sequence where you're plugging 2 into your formula. All right, let's see some examples for this. All right, our first example would be 1 over 2 to the n equals, let's start at 0 to infinity. So this is the sequence with formula 1 over 2 to the n, and n starts at 0. So this is one very compact way to get across an entire infinite sequence. This n equals 0 tells me that 0 is the first value to plug in for n here. So the first term in the sequence is 1 over 2 to the 0, and then 1 over 2 to the 1, 1 over 2 squared, and so on. Writing like this shows the pattern and shows the formula that we're using, but we could also simplify these numbers and say, okay, this is just 1, a half, a fourth, and so on. Notice that this is not unique, the way that we display this sequence. To create this same list of numbers, we could put it together in a different way. So for example, we could have this be powers of 1/2, but then we'll say n-1 as the exponent, and then n starts at 1 as the first value. This formula actually does create this exact same list of numbers in this exact same order. So these two sequences are the same. We just have options for how we list them. Let's try another one. Let's say we have n over n plus 1 as the formula. And then we'll say n starts at 1 and goes forever. If I plug in 1 for n first, I have 1 plus 1. And then the next value would be 2, so 2 over 2 plus 1. Then 3 over 3 plus 1, and so on. So this creates the sequence 1/2, 2/3, 3/4, and so on. And we can tell from this pattern that the next term in the sequence would be 4 over 5, and then 5 over 6, and so on. So I'm going to take this opportunity to talk about the factorial. It's something you may have run into before. This may be the first time you're seeing it, so I want to make sure we are in the same place. All right, so I write factorial with an exclamation point because the exclamation point is the mathematical symbol for the factorial. It comes up a lot in sequences and the rest of chapter 11 because this exclamation point, which is the factorial symbol, it's a function that you can only use on an integer. So we don't ever like graph y equals x factorial, but if you're only inputting integers like this, it actually does work. Okay, so for example, 4 factorial is something that we can compute. So what this means is 4 times 3 times 2 times 1. 4 times 3 times 2 times 1. So that would be 12 times 2 is 24. So 4 factorial is equal to 24. If you did 3 factorial, you start with the 3 and then you multiply and count down until you get 1. So 3 factorial is 6. When the numbers are really small, we can compute these by hand. If you have something like 100 factorial, that's a job for a calculator for sure, but we can at least write out symbolically like what it would be. So it's 100 times 99 times 98, and we'll say, et cetera, and you continue your pattern all the way down to times 3 times 2 times 1, and that would be some very, very large. So the factorial symbol can only go on non-negative integers. So 1, 2, 3, 4, etc. They can all be factorial. The lowest number that you can put a factorial on is 0. And this is one that doesn't really fit the pattern, but 0 factorial is defined to be 1. We'll say this is by definition. And notice that 1 factorial is also just 1. They both give the same output here. Every once in a while, we need to have 0 being plugged in here. So we go with this rule, even though it doesn't really make sense in the definition. Okay, so let's see this used in a sequence. Let's say you have a sequence n factorial, n equals 0 to infinity. So that means 0 factorial, 1 factorial, 2 factorial, and so on. Zero factorial, we said by definition is just 1. We're not going to overthink it. 1 factorial is just 1, right? And then the list is over. So this is also 1. This is 2 times 1 is 2. This is 3 times 2 times 1 is 6. And then I'll put my ellipsis in here to say continue the pattern from here. Right, so that's the last time we'll see the factorial in this video, but it will come up lots and lots of times in chapter 11. So we're only just getting started with that factorial. All right, so the ways that we've seen to represent a sequence so far are just writing out the list and assuming the pattern is clear. You can put the formula in those braces like we saw in the last few examples. There's also other weird ways that you can describe your sequence. One example is called a recursive formula. recursive formula. And the best example or most classic example of a recursive formula for a sequence is the Fibonacci sequence. This comes up in movies and TV shows a lot. Here's what the Fibonacci sequence is. A1 equals 1. A2 also equals 1. And then after that, so for A3 and forward, A sub n equals an minus 1 plus an minus 2. So this is a recursive formula because it's defining a term in the sequence as a formula of the previous terms. So an plus 1 is just the term that came before this one, and an minus 2 is the one that came before that. So let's list out some of this sequence. Okay, so this is telling us the first two numbers are 1 and 1. 1 comma 1. And then for a sub 3, we'll have a2 plus a1. So that's just the sum of these two. 1 plus 1 is 2. Okay, so now for the next one, we're again going to add the previous 2. So 1 plus 2 is 3. And now we add the previous 2. 2 plus 3 is 5. Add the previous 2. 3 plus 5 is 8. And we'll say dot, dot, dot from there. The pattern continues. We don't see sequences defined this way too often, but there are assorted options like this for representing sequences in fields. So one more weird way to think about a sequence, which will occasionally be useful to us, is that you can see a sequence as a function where the inputs are restricted to integers. We can see a sequence as a function, so like literally y equals f of x, as a function where x is restricted to just integers. I want to say integers only. So instead of y equals f of x, we kind of turn that formula into a sub n equals f of n. So typically we use x if it's going to be a continuous function. So x represents like any real number, which is what the normal x-axis is. And then we put an n as the input, like we've seen in all the examples so far, to imply that it's only usually positive integers, although technically you can start that n at various different integers and just count up from there. Let me show you what I mean in an example. So let's say we have the sequence where the formula is 1 over n, and we'll say n starts at 1 and goes to infinity. So if we wanted to write this as a function, we would say, well, f of n equals 1 over n. This is the same thing as saying the formula for a sub n, the nth term, is 1 over n. But you could also kind of compare this to the continuous function f of x equals 1 over x. These are exactly the same formula. And when you change the letter here, like to t, f of t equals 1 t, they mean the exact same thing, they make the same shape. It's just sort of this like implied mental difference now that when you see the n show up, the inputs are restricted to integers. This perspective does help us think about sequences graphically though. So f of x equals 1 over x. Get a couple of moves here. Let's say this is 1 way up here. So 1 over x, if I plug in 1, I get 1, at 2 it's a half and a third. So we get this like curve this way. If we're graphing an equals 1 over n, or you can think of it as f of n equals 1 over n, it creates the same shape. It's just only the dots at the integers, and there is no connecting curve between the dots. So you would have just disconnected dots at the integers, 1, 2, 3, etc. So at 1, this outputs a 1. If you plug in 2 for n, you get a half. And then 3 for n, you get a third, and so on. So you just sort of end up with a graph full of dots instead of a smooth curve. Where this is going to lead us now is starting to think about the limit of a sequence. And we can really lean very heavily on what we already know about the limits of functions, right? If this curve is headed towards 0 as x approaches infinity, which it is, these dots are also headed to 0 as n approaches infinity. And that's how we're going to start thinking about the limit of a sequence in class today.